Hi guys, I wanted to make a video explaining one of the FRQs from the AP Physics C Mechanics exam. This FRQ is from the 2018 Set 1 questions, and I'm doing question 2. Okay, so we can start by reading the question, and that is, two carts are on a horizontal level track of negligible friction. Cart 1 has a sensor that measures the force exerted on it during the collision with Cart 2, which has a spring attached. Cart 1 is moving with a speed of v0 equals 3 meters per second towards Cart 2, which is at rest, as shown in the figure above. The total mass of Cart 1 in the force sensor is 0.5 kilograms. The mass of Cart 2 is 1.05 kilograms, and the spring has negligible mass. The spring has a spring constant of K equals 130 newtons per meter. The data for the force the spring exerts on Cart 1 are shown in the graph below. A student models the data with the quadratic fit F equals 3,200 t squared minus 500 t. All right, now let's get started solving this problem. So for part A, it says, using integral calculus, calculate the total impulse delivered to Cart 1 during the collision. So we want total impulse. All right, well, we know that impulse is equal to change in momentum, which is equal to the integral from T0 to TF of force across time. All right, so, and we want to be using integral calculus. So for part A, I know this is true for my impulse. And so because I don't have any information really about momentum, because I don't know the final velocities of my cart, I can use just impulse is equal to the integral of force dt. All right, so now in this question, to find force, we're given an equation right here, and we're given this graph. So to find my T0 and TF, I'm going to use this graph. All right, so if I sketch a parabola, and so for my T0, we want to find at the instant, right when the cart hits the spring. So that'll be at t equals 0 in my force versus time graph. And for my T final, we want to see right where the spring detaches and stops exerting a force. So this will be my other x-intercept, where force equals 0. And I would say 0.16 is a fair estimate for that value. Okay, so now I'm just going to plug in 0 to 0.16. And you are allowed to have your calculator on the exam, so just put this force equation into the integral, and you would get that this is equal to negative 2.03 Newton seconds. All right, we're done with part A. For part B, it says calculate the speed of Cart 1 after the collision. All right, so for the first part of part B, we want to calculate the speed of the cart after the collision. All right, so like I said above, I know that impulse is equal to my change in momentum, which is equal to the integral of force across time. But I want to find the speed of Cart 1 after the collision. So what I can do is I know that momentum is just mass times our final velocity minus our initial velocity. So using my impulse from above, I can say that negative 2.03 is equal to my mass 1 times its final velocity, which is what we're solving for, minus its initial velocity. Okay, so then I get that we have negative 2.03 plus our mass 1 times v0, all divided by mass 1. And if I do this on my calculator, we know that v0 is equal to 3, mass 1 is equal to 0.5. So if I do negative 2.03 plus 0.5 times 3 divided by 0.5, I get that my final velocity is equal to negative 1.06 meters per second. All right, so then my second part of part B is just asking in which direction this car would move after the collision. And we see that our velocity is negative, so I can go ahead and say that we move to the left, because in this scenario, we're designating the left as being our negative direction. All right, moving on to part C. Part C says calculate the speed of cart 2 after the collision. All right, so let's do that. So in part C, well, it's important to know that this is a collision, and in every collision, momentum is conserved. So I'm going to start by saying my initial momentum is equal to my final momentum. All right, now let's specify this a bit more. We know we have cart 1, the momentum of cart 1, which is mass 1 times v naught, and we know that our cart 2 is initially at rest, so its velocity will be 0, and so it will have no momentum. So that looks a bit more like a sigma. Oh, boy. Okay. Plus 0. And then finally, we know my mass 1 times my VF1. And then we know that cart 2 will have some final velocity after the collision, so we can start by solving for that by saying m2 times VF2. All right, so now I'm just going to rearrange this and say that m1 v naught minus m1 vf1 over m2 is equal to my final velocity 2. All right, so if I put this all into my calculator, I would get 0.5 times 3 minus 0.5 times negative 1.06 over 1.05. And I get my final velocity 2 as being equal to 1.93 meters per second. All right, so that was part 1. And then for part 2, show that the collisions between the two carts is elastic. All right, so to show that the collision between the two carts is elastic, we're going to say, this was part 1, and now we're on part 2. To show that this is elastic, we need to say that our initial energy was converted entirely into our final energy. All right, so now my energy initially is just my kinetic energy of my cart 1, because cart 2 is just at rest on the ground. There's no work being done on it. All right. So I'm going to say that I just have kinetic energy 1 initially. And then finally, we know both our carts have a velocity. We're going to look at this after the cart has let go of the spring, so we don't have to worry about any spring potential energy in this. So I'm just going to say that my K1 final plus K2 final. All right, so now we know that initially my kinetic energy is 1/2 m1 v naught squared, and that has to equal 1/2 m1 vf1 squared plus 1/2 m2 vf2 squared. All right, so then I get that 0.5 times 0.5 times 9. So this side's equal to 2.25 joules. And to see if we get the same on the other side, we would have 0.5 times 0.5 times 1.06 squared plus our 0.5 times 1.05 times 1.93 squared. And we get that that is equal to 2.24 joules. And I'll change my equal sign into a squiggly sign, because even though this isn't exactly equal, we did round in our previous equations, and so we're getting that these are approximately equal to each other, this is within rounding, so this is an okay thing to say. All right, moving on to the final part. So for part D, we need to calculate the speed of the center of mass of the two-cart spring system. Okay, what's important to know is whenever you are calculating the speed of the center of mass of any system that undergoes a collision, the speed of the center of mass will always be conserved. So it doesn't matter whether you're looking at the system before or after the collision, you're going to have the same speed of the center of mass. Okay, so to make this easier for myself, I'm going to look at before the collision, when only my cart 1 is moving. So therefore, we know that my speed of the center of mass, well, that will be equal to my mass 1 times v naught plus mass 2 times, well, its v naught's 0, so this whole term goes to 0, divided by m1 plus m2. This is just using our equation for speed of center of mass. All right, so then if I put this in my calculator, I get 0.5 times 3 over 1.55. And I get that my speed of the center of mass is equal to 0.97 meters per second. So I think this is one of the most important takeaways from this question, is that whenever you're looking at the speed of the center of mass, it is always conserved, so you can look at before or after the collision occurs. All right, now part D. Calculate the maximum elastic potential energy stored in the spring. Okay, so this part is also a little tricky, but we can do it. Okay. So we want to find the maximum elastic potential energy stored in the spring. So therefore, I'll have another energy initial equals energy final, because if we're looking for the maximum amount, this is if 100% of my energy is conserved. So now I can specify this a bit more by saying my initial kinetic energy just from my first cart. Well, now this is where it gets a little tricky. We know we're going to have spring potential energy, so we can add that in right away. But then I have to also account for the fact that when this spring is being compressed, these carts are moving in this collision. So then I get plus the kinetic energy of cart 1 and cart 2. Okay, so now I can say that 1/2 m1 v naught squared equals spring potential energy plus, okay, so we know I'm going to have 1/2 m1 plus m2, because when this spring is fully compressed and it's at its maximum spring potential energy, that is when these carts are almost like one unit. They're acting together. And so while these carts are together, we need to think about their velocity at that time. Well, luckily, in part 1, we calculated the speed of the center of mass for this 2-block system. And so my speed of the center of mass is always conserved before, during, and after the collision. So I can just put this value in here. So I get 0.97 squared. Okay, so now if I add this over, if I just subtract that from both sides, I get spring potential energy is equal to 0.5 times 9 minus 0.5 times 1.55 times 0.97 squared. All right, and I get that my spring potential energy is equal to 1.52 joules. All right, and that's it for this question. We've done every part. This video took about 13 minutes, so we would be on track if this was during the test. Keep in mind that for every FRQ, you're not expected to get a 15 out of 15 on every single one. Really, if you're able to get even just like a 9 out of 15, that's great, and you should be proud of that. So I hope this video is helpful, and I'll see you in my next video.